Okay, Physics 12. This is going to be our lesson on collisions in two dimensions. Okay, so in our last lesson we were looking at conservation of momentum, and all of that was done in one dimension, and this is where we kind of amp things up quite a bit, and we start looking at what happens when collisions are happening in two dimensions and not just on a linear straight line. So here we go. All right, so again, as just mentioned, obviously not all collisions are going to happen in one nice straight line, one-dimensional scenario, right? Not everything is a head-on collision. So we mean a very brief example too would be talking about like playing pool, right, or billiards, right? When you take that shot, rarely do you try and hit something straight on and then have, one go straight and one come right back, right, at an exactly 180-degree angle, right? Often you're using angles to try and figure out, okay, if I hit at this angle with this, type of force, which way will it go and how will the other ball react, right? Because even while you're trying to sink one, you're trying to make sure that you don't sink your cue ball at the same time. Okay, so being able to kind of play with those angles and about, what speed you're going to hit the ball with and all that kind of stuff, that's all kind of part of this physics lesson on collisions in two dimensions. You're going to see a lot of things similar to when we did projectiles, right? When projectiles were happening in two dimensions, we had to think about, well, what was happening in the X plane and what was happening in the Y plane. Same kind of stuff is going to happen in this lesson when we talk about collisions in two dimensions. What's happening with the velocities in the X, what's happening with the velocities in the Y, and how conservation of momentum is preserved within the X plane and within the Y plane, and then kind of putting them all together after the fact. All right, so we'll be doing a lot of vector components in this particular lesson. So this particular example is one we'll do later, but just kind of looking at if we were thinking about like a particular car collision, right? And this would be what people who analyze accidents might start looking at is which cars were they? What were the mass of the cars? Do we know what speeds they were going, or can we calculate what speeds they were going? Looking at the skid marks, can we figure out when they were braking? All that kind of stuff, right? But in this particular example, you can see that one car is headed directly north. One car is headed directly east, and there's a collision here that kind of happens at the origin, and then they kind of lock up and both move away in a particular direction. Okay, so the person analyzing this particular accident might try to figure, well, who was at fault here, right? Maybe if this was just a regular intersection and no one was at a stop sign per se, who was potentially speeding, right? And that's what we'll look at later in a minute, right? But what happens, like I said, in this collisions with two dimensions, right, the total momentum of the wreck, right, is going to come through using that law of conservation of momentum. And again, as I mentioned, right, with that, it's known that the wreck's northern momentum is equal to that of car A prior to the crash, and similarly, the wreck's eastern momentum must be equal to that of car B prior to the crash, right? So again, you're thinking of things in those two dimensions, right? So with the eastern momentum, we're looking at car B because car B was the one that was actually moving east, right? And only east. It only had an X momentum, right? Or velocity in the X. Same with car A, right? That's going to be northern. So whatever this is, northern momentum, is going to be equal to that of this car here because this one doesn't have any northern up and down momentum, right, or velocity, okay? So this is, again, going to be a huge aspect of using vector components and looking at things, well, what is it in the X? What is it in the Y? What's the resultant vector? How can we break that up into its component parts and then, use the component parts and then come back to a resultant value at the end, okay? So we're going to look at two examples. They can get quite lengthy. There's quite a bit of work to them. So we'll only be going through two together in this video, and then you're given 3 to practice, right? And each one will probably take you about 10 minutes, okay? And here we go. All right, so what we've got in this first one for a sample problem is we have a billiard ball, right? So we're playing pool here, that has a mass of 0.155 kilograms, and it's rolling directly away from you at 3.5 meters per second, right? So we're kind of considering us here, like in terms of frame of reference, this is us here, and the billiard ball is moving directly away from us here, okay? And it collides. I don't know why we have a stationary golf ball on our pool table, but we do. But it collides with this stationary golf ball that has a mass of 0.052 kilograms. So to start this, it's this ball that's moving and this one's just sitting here. Then there's a collision, right? When they collide, the billiard ball rolls off at an angle 15 degrees clockwise from its original direction. Okay, so the original direction was again going straight this way, straight up. So if we rotate 15 degrees clockwise, it's now going this way, and that speed now is 3.1 meters per second. So we do see that it has definitely lost some speed, right? It's lost some momentum because some of it's been given over here, right? Because now the golf ball has picked up speed and is moving from its stationary point, okay? And what we're being asked is, well, what is the velocity of the golf ball? What is this speed? You know, what angle is it being sent off at, and with what velocity, okay? So this is where we start getting into things. All right, let's switch to my video. So like every other physics problem we've ever done, we start by listing the things that we know, right? So we can call the billiard ball the mass of A, and we can call the golf ball the mass of B. So things that we know that the mass of the billiard ball, so the mass of A is 0.155 kilograms, and we know the mass of the golf ball is the 0.052 kilograms. Okay, we know the initial velocity of the billiard ball, which is the 3.5 meters per second, and we'll give that a positive value because it was heading away from us, right? It was going up, right? Even if you go back and look at the diagram. And the velocity of the golf ball, at least initially, was 0. It was stationary, 0 meters per second. Now, we also have that the velocity prime, so the velocity after the collision of the billiard ball, is 3.1 meters per second, right? And, you know, at the direction of 15 degrees clockwise, okay? And this is the velocity that we're trying to find, right? That's our unknown, okay? So that's our starting kind of list of the things that we have and the list of the things that we don't have. Now, like I mentioned, with something like this, right, because this is not just a straight up, straight down, we now have it at an angle, we need to incorporate that angle by breaking things up into its vector components. So let's just look at our billiard ball in this case, right? So what we have is this ball that is now moving here, right? And this is a value of the 3.1 meters per second, right? And it was facing straight, where that was a 15-degree angle, okay? Now, typically in standard calculation of vector components, we like to look at everything in relation angle-wise to where the imaginary x-axis would have been, right? So if that's 15 degrees, 90 minus 15 is going to give me an angle of 75 degrees. And that's the angle that we'll use to calculate our vector components, right? So we have a velocity in the x, right? So we'll actually call that VAX, well, V prime AX, I should say, right? Is this value here. And then we have this y component, which would be the V prime AY, okay? So that was our resultant velocity, right? So we're now breaking that into components. What is the velocity in the x, right? And what's the velocity in the y? And we can solve those things now by just using our basic trig SOHCAHTOA, okay? So again, by setting it up this way, we're always using cosine to find anything in the x, and we're using sine to find anything in the y, right? You could have used the 15 degrees, but then you would have been using sine for x and cosine for y, which it's just easier to keep everything standard, cosine for x and sine for y, okay? But it does work either way mathematically, okay? It wouldn't be wrong. Just a lot of people like to keep things consistent. So in doing that, like I mentioned, so our V prime AX is going to be done by calculating cosine of 75 degrees times the 3.1. Okay, and when we do that, we get a value of 0.802 meters per second, right? And that's in a positive direction, right? So we'll just leave that as positive there. And then our V prime AY is going to be from sine of 75 degrees times our 3.1 meters per second. So when we do that calculation, we get a value of 2.99 meters per second. And again, that's positive because it's going straight up, right? I mean, you can kind of go back and think about this in bearings again, and you could say that this is north and this is east, but we can just kind of leave them right now as positives because we weren't given the question as bearings. It was more about clockwise or counterclockwise angles. So that's how we'll give our final answer at the end. Okay, so that was kind of step one, right? Let's get our component parts of the result there, right? So now we kind of have all these extra variables, right? Extra knowns that we've now got, right? So we still have our mass of both of the balls, right? We have our initial velocity here, right? And then we've got our final velocities in each of the components. So what we need to do now is look at the component parts of that other velocity, right? So here, this was stationary. So VBX is 0, VBY is 0, right? If we looked at the initial velocity in terms of its x and y component parts, right? If we break this down, right? The velocity of A in the x is actually 0 because that billiard ball was not moving left or right. It was just moving straight up and down. So its velocity in the x is nothing. However, its velocity in the y is exactly what it said because it was moving straight up. That's a value of 3.5 meters per second, right? So when we go to start this, and obviously I'm going to have to erase this, but when we set up our first law of conservation of momentum, right, using that law of conservation of momentum in each of the components, if we start by looking at what's happening in the x, we'll obviously need our mass of A, our mass of B, and now we'll need velocity of A in the x, velocity prime of A in the x, velocity of B in the x, and velocity of B prime in the x, okay? So anything with x is what we're using. So we would also need this one, right? And we would need this one. And again, since this is stationary, we can make the conclusion that, well, VBX is 0 and VBY is 0. Okay? So these are going to be the key ones we're going to use, right? So when we do MAVAX plus MBVBX is equal to MAV prime AX plus MBV prime BX, the thing that we're trying to solve for ultimately, right? And we'll do this with X, then we'll do it with Y, and then we can put that together in a nice little right triangle and figure out what is the overall resultant velocity there. Okay, so let's just get into that, right? So I've copied all this down onto my handy-dandy piece of paper so I don't have to kind of go back to the slides. All right, so here we go, using those values. So let's look at it. Again, we're looking at it in its two dimensions, so we look at it in each of its component parts. So we'll start with what's going on in the x. Okay, so we set up our law of conservation of momentum of what's happening in the x-axis. So that's MA VA x plus MB VBX is equal to MA V prime AX plus MB V prime BX. Okay, so again, things that we already knew, right? We had this mass. It was 0.155 kilograms. I'm not writing my units because I legitimately do not have enough space on this whiteboard to do it. Okay, that's why I'm being bad with this. Okay, our VAX, right, was actually 0, right, because it initially wasn't moving this way, right? Our mass here was our stationary golf ball, 0.052 kilograms, and its velocity in the x is 0 because it, again, wasn't moving, right? Here, again, mass of our billiard ball, 0.155 kilograms. The V prime AX, we solved for that on the last whiteboard slide, which was the 0.802 meters per second. Okay, and then this mass, right, I'm going to have to do this and I hate it, but was the 0.052, and this V prime BX is part of the thing that we are going to need to solve for the overall V prime, right? So this is our unknown. This is what we're solving for. So what's nice is that gone and gone, because they're multiplied by 0, multiplied by 0, So I can get this value isolated on its own by subtracting this entire term, bringing it over here, right? And then dividing by this mass value. Okay? So we multiply that together, we do the division, and we get a value here of negative 2.39 meters per second is equal to our v prime of the golf ball in the x. This makes sense that it's negative because if you go back to kind of our original diagram of what was happening, the golf ball was here and it got kicked off in a direction this way, right? So even just by looking at the diagram, it kind of made sense because, well, we knew that the billiard ball went up and to the right, so it's going to go off to the left, right? At least somewhat of what, right? So it does make sense based on the diagram they've at least given to us. So again, that's something we need to keep in mind. So this is important. Make sure we write this down or circle it somewhere so we know where to find it on our page when we need it again. Now we do the same thing, except with the y component. I'm going to try and save myself some time here and only erase what I need to. So y component, set up the same law of conservation of momentum, except everything that once was an x is now a y. Right? B-A-Y, and B-Y, and B prime A-Y, B prime B-Y. Okay, now when we go to fix this, okay, thing is that for our first one, our velocity in the y wasn't 0, it was actually the 3.5 meters per second. So I can still have this 0.155 kilograms here, but the velocity of the billiard ball, the first A object in the y component, was straight up 3.5 meters per second. The mass of the golf ball stayed the same. The initial velocity of the golf ball in the y is still 0, thanks to the fact that it was stationary. The whole thing was stationary from the beginning, right? So it didn't move. And again here, this is where we need to make some changes. So I'm going to just erase this whole thing. All right, so with this one, again, your mass didn't change. It's still that 0.155. Our final velocity, okay, in the y was what we calculated on that first whiteboard, and that was that value of 2.99 meters per second. Right, and this is now being added to the mass of the golf ball, the 0.052 kilograms, and then this v prime by, which we don't know and we need to solve for. Once again, this cancels because it was stationary, so multiplying by 0 gives you nothing. And then what we need to solve for is this v prime by. So what we need to do is take this, subtract this value, right? Bring this over here, and then divide by this mass, okay? So this is the formula you end up with, 0.11155 times 3.5 minus the 0.155 times 2.99, all divided by the 0.052, and that will equal my v prime by. Do the multiplication, do the subtraction, do the division. You get a value of 1.52 meters per second is equal to that kind of final velocity of the golf ball in the y. Again, an important thing that we've just solved for. So now what we have is we have the components of the golf ball's kind of velocity that it went off, right? We know that it went off at 1.52 meters per second in the y, and it went off at that negative 2.39 meters per second in the x, okay? So we want to figure, well, what is that as a result? And what about, what is that as an overall angle? What is that as an overall velocity? Right angle triangle, here we come, right? Put the components together. All right, so at that point, we know that our lovely little golf ball, right, when it went off, it went in the x, negative 2.39 meters per second, or 2.39 meters per second off to the left, and we know that it also went 1.52 meters per second up, right, because that value ended up being positive. We are interested in what is this value here, right? What's that? Pythagorean theorem, right? So that's going to be the square root of the sum of these squares. Squaring the negative is just going to make it a positive, so it's not going to matter. And we get a value there of 2.8 meters per second. My solutions in the slides, I'll give you a heads up. They say 2.83 because I was bad and forgot to look at my sig figs. My bad, sorry. Should be just 2.8. My answer shows 2.83. Not rewriting the whole thing, sorry. Okay, so there's your 2.8 meters per second. Got that part, but it's a velocity, it's a vector, it needs a direction. It goes 2.8 meters per second. Where? Well, let's figure out what this angle is here, right? Opposite, adjacent, use tan inverse, right? So theta is going to equal tan inverse of opposite, 1.52, over adjacent. Remember, use your absolute values when you're doing this, okay? So we'll just use the positive 2.93 because we're just looking at the ratio of the sides. We're not interested in kind of what angle quadrant we end up in. So just use your positive values. You do that, you get a value of 32 degrees. All right, so our final answer is that the golf ball heads off in a velocity of 2.8 meters per second, 32 degrees. So it was here, and now it's gone 32 degrees clockwise from its original position. All right, so there's one done. So as you can see, this is why we're not going to be doing a whole bunch of these on this video because they take a while to do. Okay, but just break it down, look at it bit by bit, and you will be fine. All right, so like I said, there's kind of the solutions that I just wrote down on a piece of paper. These are the ones that I was referring to when I did these notes. Again, you will see that I've kept things with 3 sig figs because I kind of didn't look, I'll be honest, when it should have just been 2. So it should have actually just been, this angle ends up being like 32.4 something, like 4.8, so I rounded to the 5, but it should have just stayed at 32, and that should be 2.8 meters per second. Okay, so again, this would be one where if you already feel comfortable with this, by all means, pause me right now and just off you go, see if you're good to go and see if you get those answers. If you're already kind of looking at this going, nope, wouldn't know how to do this, I'm just going to watch for an entire other example, then keep tuning in. Okay, so here we go with this problem. So this is the one that was shown in the diagram at the beginning of the slide, right, referencing this car collision. Okay, so here the police are investigating an accident pictured above. Using particular data tables, they have determined that the mass of car A, right, the one traveling north, is 2,275 kilograms. The mass of car B is 1,525 kilograms. From the skid marks and data for the friction between tires and concrete, right, so all of the other calculations that they've done, the police have determined that the cars, when they were locked together, had a velocity of 8.6 meters per second. So this motion up here, right, this is 8.6 meters per second, right, at an angle 43 degrees north of the eastbound street, right? So the theta that they see in that direction, right, so it's kind of like east 43 degrees north, right? That's the direction they're headed. If the speed limit was 35 kilometers an hour on both streets, right, so the north-south street and the east-west street, should one or both cars be ticketed for speeding? Okay. So, once again, let's start writing down the stuff that we know from this problem. So, things we know. Car A has a mass of 2,275 kilograms. We also know that car B has a mass of 1,525 kilograms. We do not know the velocity of the first car. It is unknown, right? This is what we're trying to find. We're trying to figure out what it's speeding. However, what we do know is that if we were to think about that first car, which is traveling north, right? If we were to think about that velocity in terms of its component parts, we know that its velocity, initial velocity in the x, would have to be 0. And again, all this would be in meters per second. We'll have it convert to kilometers per hour at the end. And this is the thing that we're unsure of. We're really specifically interested in VA in the y, because we know that that car was traveling north. Okay? Same type of thing applying to car B that's traveling east. Right? We don't know its velocity. Right? The velocity of B is unknown. But again, you can break it up into its component parts and think about the fact that, oh, well, this is the thing we don't know, but we know that its motion in the y initially is 0 meters per second, because it was never traveling at a northern direction. It was initially just traveling east. Okay, so again, thinking about things in its component parts. Then we talk about the resultant, right? We know that the v prime velocity of A is that 8.6 meters per second at a direction of east 43 degrees north, and that's actually the exact same as what just the overall velocity of B is after they collide, right? So V prime. All right, and those would be the same things. However, because we're really interested in just what VAY is and just what VBX is, right? These are our two real unknowns that we're looking for. Okay, we need to again go back into component parts. So this is all well and good for what the V prime is, but let's look at, well, what is V prime X and what is V prime Y? Okay, so again, we go component parts. So we have the following diagram, right, because it was east 43 degrees north, so you get something that looks like this. That's your 8.6 meters per second. So east and then 43 degrees north, so there's my 43 degree angle. So I'm interested in these two things. What is V prime AX and what is V prime AY? And again, because the cars are collided and they're stuck together at this point, V prime AX is the same as V prime BX, and V prime AY is going to be the same as V prime BY. Okay, so that needs to be clear, okay, because they're locked together at that point. So even when looking at them in their final component parts, right, they are the same in that aspect. Okay, so from there, we now break it down, right? Let's just look at what's happening with the X component, which will solve ultimately for the speed of the B car, and then we'll look at it in the Y component, which will solve for the speed of A car. All right, so here we go. X component first. Again, it doesn't matter the order you do this. You can do this in X component or you can do this in Y component first. It's just I start with X all the time because that's how I graph things, X, Y. So why wouldn't I? So again, you're still using that law of conservation of momentum. So MA VAX plus MB VBX is equal to MA V prime AX plus MB V prime BX. Okay, so again, you can rearrange this first, right, knowing that what you're ultimately solving for is this, right, or you can start plugging things in first and then maybe rearrange a little bit later. Okay, I like to plug things in first just so I can see where anything zeros are going to cancel out, and then I rearrange once I have that. So here, things that we can fill in. I have that this mass is 2275, and that this initial velocity of car A, which was going north, is 0. Mass of car B is our 1525, this is what we want. And then these were the things we found in our component parts, right? So again, this is going to be our 2275 times that value that we just solved for, which was the 6 point. I didn't actually solve for those, did I? Well, I should have solved for them using sine and cosine. But had I solved for them using sine and cosine, I would have gotten 6.29 here, plus, and then this is the mass of B, 1525 of, again, the same thing, 6.29. So just quick sidebar, because I realized I completely missed this part of the calculation. When we did this, right, and I demonstrated this and called this our, we knew that this was our 8.6 meters per second. We had that this was a 43-degree angle, right? This is our V prime AX, which is also the same as our V prime BX. And then this vector component part here was our V prime AY, which is the same as our V prime BY. And I solved for these using my basic trig, right? So this is going to be equal, so the X component part is going to be cosine of 43 degrees multiplied by your 8.6 meters per second, and that gives you a value of 6.29 meters per second. Okay, and then this Y part, right, so V prime AY, which is the same as V prime BY, is going to equal your sine of 43 degrees multiplied by your 8.6 meters per second. And when we do that, we get a value of 5.865 meters per second. I'm just going to keep those extra decimal places going through. Okay, sorry about that, but that's there. So this is where that 6.29 number is coming from. So now, once you go back to your law of conservation of momentum formula, you realize the only thing that you have left to solve for is this VBX. Again, this is 0, this is gone. This you just multiply, and add, and then you just need to divide by the 1525. So your calculation here ends up being your VBX is equal to your 2275 times your 6.29 plus the 1525 times the 6.29, all divided by 1525. You do all that wonderful math, and you get a value of 15.67 meters per second. Right? And then we know the quick little trick from going from meters per second to kilometers per hour is just to multiply by 3.6. You do that, and you get a speed of 56 kilometers per hour. So right away, we know that car B is getting a ticket, or would be considered at fault, providing there were no other yielding stop signs or whatever. Okay, but the question didn't just ask what was car B doing; it was also should both be getting the ticket or just one. So now we go and figure out what was going on with car A in the Y component. All right, so again, save just a minute. Now we do a Y component. All of these X's turn to Y's. Obviously, masses don't change in 2 dimensions. It's still the same, but there we go. So again, with the Y component, our mass is again still 2275, but our velocity of A in the Y was that initial speed it was going, which actually, wait, that we still don't know. Mass of car B is our 1525, but the velocity of car B initially, since car B was doing this, is nothing in terms of the Y. It wasn't going up or down at all, so this is 0. And then once again, this is our 2275. This was found using the vector components of the triangle that I just did, which we had that value there of 5.865. And then it's plus that mass of B, which was the 1525, and then it has the same, since they're locked together, their final velocities are the same in both X and Y, right? So again, this whole term is gone because it was multiplied by 0. This is what I want, so it's the same type of thing. Multiply, add, divide by that. So your VAY is equal to your 2275 times your 5.865 plus your 1525 times your 5.865, and then all of that divided by your 2275, which means your starting velocity of the car traveling north in the y ends up being 9.796 meters per second. To put that in kilometers per hour, you multiply by 3.6. I think it ends up coming out to like 35.3 kilometers per hour, but technically we're in 2 sig figs. So the velocity of that car A traveling north is just a nice 35 kilometers per hour, which is technically the speed limit, so no ticket. Okay, and that's that. So, here's my slides. That's where we're getting those values from, right, of 35 kilometers per hour for car A going north from the Y component, and car B being the 56 kilometers per hour going east, so car B would be the one that gets the ticket. So with this, it's all kind of coming back to, again, your vector components, right? Break it up into your X, break it up into your Y, right? Sometimes it's helpful to make a table of all the things that you have, right? Even if you just start off with a general table that's like everything in X, everything in Y, and just kind of start filling everything in. Sometimes that's really helpful for people. And then it's just, you know, sometimes, like in the first question, we had to, you know, use the initial information and then get the component parts to figure out the resultant velocity, right? In the final, in this case, you had the final and you had to work backwards to figure out those initial values. Again, every question is just slightly different, but using that main law of conservation momentum, but now in 2 dimensions. So thinking about what's happening in the X dimension, what's happening in the Y dimension, and then being able to combine them at the end or use their end to rework and get the beginning. Okay. Again, there's a nicer just typed in velocity of formulas of what's going on, where they've just kind of put in those vector components right into the formula itself. I find people, when they look at a solution like this, they kind of go, wait, what? Why? Huh? Wait, what? Why? But if you break it down, it makes more sense. Okay, so again, like I said, you've just got 3 questions to try and take a look at here to see how you're feeling with this collisions in 2 dimensions stuff. In your textbooks, it is page 509, questions 35, 36, 37. Because of the different version that I have, it's all the same questions, but the solution set that I have will say something like questions 12, 13, 14, or 13, 14, 15, but it's the same order, okay? And I'll just make a note of that on Google Classroom so you're also aware of that slight discrepancy. Again, if you don't have your textbook with you at this point, please just reach out. I can send you the PDF copy of the version that I have. Again, it's the same questions, just slightly different. All right. So that's collisions in 2 dimensions. And this is kind of what that virtual lab that I'm hoping I'll be able to assign will be on, where you'll be able to kind of look at, you know, objects hitting each other and how we can, you know, analyze what's going on there. But I'll get you more information on that soon enough.